Okay, welcome to core concept 10. And as I discussed, as we talked about moment and the effective forces in turning an object, this is where we get into circular motion. This is also part of further mechanics 2, the second part of the further mechanics curriculum, right? That's where we start. Circular motion. And this is, you can see I've tried to make a few circles and arcs here. We'll put them to some use in a bit. But what I wanted to first show, and here I have a string, and just kind of go through this whole idea. And this is really what we're doing, an object that's spinning. And as you can see here, uh, I have circular motion. So this little piece of metal I have on the string is moving in a circle. And that's the motion we want to study. Our classic case has always been to study, what happens if it's linear in a straight line and if it's balanced out, what's going on. But here, what we're going to do is that. And in the initial case, I'm just going to talk about horizontal circles. So I'm not going to take the effect of gravity. So I'm just going to go in a horizontal plane, right? But then I'm going to look at it from top, and then I get this view. We'll start off with some basic ideas first, right? So let me just make this my little particle here. Hopefully that's visible, right? And it starts off, and if my direction of motion is that way, right? So this is the spin that I'm viewing from top. There is no effect of gravity. We'll, just as we did with everything else, we'll build gravity in later. But for now, it's just that's my particle, and of course its mass is m. If we'll see whether we need that. And we're going to set the radius of the circle in which it moves. I use another color to define that radius, the circle of radius r, right? And we're going to give this object a velocity of v. Now, this is the velocity with which it moves along this circular path. And we're going to take a look at a few equations that you should have some idea of the math behind it, but let's give it a shot, see where we get with that. So first, if an object moves along a circular arc, I will just define a line here and an angle theta, okay? I'm going to define that, and then I know, if I just have these little X marks here, I know this is R as well. If I define this as A, and if this is B, we know that the distance AB, not the straight line, but this arc, is a distance of S, and that can be written as R times theta, but mind you, theta is in radians. In radian, not degrees, right? And just so you know, pi radians is equal to 180 degrees. Just remember that. So 2 pi is a full circle, and we know that 2 pi r is the circumference of a circle with radius r. So that's this relationship. Now we know if in time t, velocity can be written as s by t. So that is clear. But what if we now want to find out in radians how much of that circle did this object traverse? How much of this, what is this, like, to define if this is a piece of pie, what's that angle? And if you want to achieve that, the angular speed, as they call it, angular, right, would effectively be the first differential of theta here. That's what's moving by time, which is how much of theta in what amount of time, right? I could say, I'll just say here, this is effectively just ds by dt, right? That's the change in distance for the change in time. That's what it is, right? Now, if I go back here and substitute theta would be s by r, which would be, if theta is s by r, because I'm not using delta, theta, and delta of time, just using theta and time, I could just write this as 1 by r, that's theta, times s by t, because s over r would give you theta, which would then mean the angular speed is equal to velocity by radius. So this velocity by radius will give you the number of radians per second. Now you'll find textbooks that denote this as theta with a dot. You'll find some that would call it, I'll use some different colors for the notations. You'll find some that call it theta with like a prime. But a common notation for angular speed, also called angular velocity, is this sign W, which is also the lowercase of the Greek alphabet omega. So this is a common notation. Okay. I think this is the key that, one of the most important pieces that come up, and you'll find all kinds of problems that state these in different aspects. But a common way in which you'll find a problem talk about W is by referring to it in RPM, which is revolutions per minute. So if I defined 1, if the RPM is 1, it's like 1 revolution in a minute. That's nothing but 2 pi divided by 60 radians per second. So remember that. I think this is very valuable because you'll find questions which pose this in RPM. So another valuable piece to keep in mind, right? The relationship between theta and how it's represented. I think this is very useful. So I'll probably just take out a lot of this and just leave you with a formula there, and that is known. So all of that can go. We'll just get back to what's important. Theta is equal to s by r, and theta prime is equal to velocity by r, also denoted as W. You have all kinds of variants of the formula. W is equal to, linear velocity is equal to angular speed times radius, another very common means of representing it. So a bunch of different formulae that you can sort of keep in mind, right? Now I want to look at this a little closer, and that's why I have this picture here, right? And if you take a look closely, let's say I break this down into 3 pizza slices here. And if I observe very closely, and I draw, let's say, this sort of an axis system, you can see here there are equal amounts of time. I'm going to just extend this here. Extend this here. So assuming these are equal, in the first instance of time, these pieces of the arc are of the same length s. So S1, S2, and S3, S1, S2, and S3 are all the same. However, the displacement along, if this was x and this was y, the amount of time, let's say an object is moving this way, in the first piece of time, it covered a value here, but a much higher x-axis. So it creates sort of an interesting fact to observe that for somehow, whilst overall velocity was just constant, right, which means velocity is constant, radius is constant, angular speed is constant. So all of that being constant, we can still observe as we look at this horizontal plane, one of the axes is moving faster than the other. So a component of displacement seems to be changing much faster than the other with respect to time. So if I look at the x component, the first piece of time, x moved by that much. The second one was that, and the third was much larger, assuming this is the direction of motion. And if I look at the y component, it actually is slowing down in the 3 pieces of time. Their net values don't change because in the first instance, we had a small x value, much larger y. The next one was roughly the same, and then the x, large x, and a small y. So if you treated them as vectors and did the math, it would still be great. But the point still remains is there is a change in the velocity along when the velocity is, or rather there is a change in the velocity and there's a change in displacement, which translates to velocity. There's also a change in velocity because you're now seeing greater lengths covered as time progresses. So it's almost as if as time progressed, you're just increasing your velocity, right? Because of the same unit, you covered this much, the next unit covered this much. So that means there was an increase in velocity. And when you have increase in velocity, there's a function of acceleration. Where is the acceleration? We just said this was v is constant. And I think it's valuable because you want to understand this in a sort of intuitive way, that if I had an object that was just moving, and if I just take, let's just take an object that's moving, and I tried to apply a force to it for one instance, then you'd have some kind of a vector, and you'd see that it would result in a shift. The resultant vector would shift. But if this force continued to apply all the time at the same angle, then what would happen is it would turn. By corollary, and actually maybe the way to treat it is also, if I just took this piece and if it was projected straight, but I swung it, you see, as soon as I give it some pressure with the string, it wants to create a circular motion. So as soon as there's a motion this way, when there's a slight tug, it decides to make a nice smooth curve along this piece of string in my hand, which is radius. So it appears like that force component directed towards the center creates this curve. If a force component is directed, that means there is an acceleration, and that is what this acceleration means. So when I see velocity changing along the individual axis of motion, I can arrive at a calculation for acceleration. Now we want to see what's going on, and we want to use this example to see how to make how we make sense out of it, right? So let's just take this picture, and maybe we'll draw it here so that it's a little more a little easier to understand, right? Let's just maybe we'll leave that there. We'll take let's go back. Let's go to green. Let's draw this line here. At this point here, let's say I have a velocity vector, right? And I'll retain blue for this one. Also R. And then let's say some time passes and I get here and I have a small angle again. Maybe I'll call it alpha. But when I'm here, I will have, let's say, a tangential component of velocity. Now I want to, let's assume this is a very small, I'm just zooming into a very tiny piece of this. And if this is, let's say, u, what might be happening here? The velocity here is also u. However, it has two components. Let's say component along one direction, and I should use velocity still u. It has a component here and a component here. And let's try to see what happens to each of these. So if this is alpha, what would this angle be? So this is where geometry is really, really useful. This would also be alpha, which means this would be u cosine alpha, and here I would have u sine of alpha. Let's try to resolve this a little bit and see what's happening to the two pieces of velocity. Let's take a look at it first along the x-axis. So what's the change here? Along the x-axis, change in velocity, delta u along the x-axis is equal to, I should probably, not the most convenient. Delta u along the x-axis divided by delta t, which is change in time. So, right, so I'm just going to use t for that, and then I'll just call that acceleration along the x-axis. Maybe that's the right term. Okay. This is nothing but final velocity u cosine alpha minus u divided by time. And conversely, along the y-axis, which would be delta u along the y-axis by time, is nothing but u sine alpha minus, what is the component of u here along sine? It's nothing, it's zero, because this is the axis, so this would be time. Now, if alpha was a really, really tiny angle and zoomed it here, if it's super tiny, right, we could use limits. This is ay. Let's say we use limits. And you should, in most high school mathematics curriculum, they should have taught you limits. And if they haven't, then perhaps the easy way to understand this is, maybe come back here. So if I do this and define alpha, so this is the sine component, and this is the cosine component, assuming you have an R here, right? If alpha became really, really tiny, as alpha just got like really close, if I came really, really, really close, but not zero, you would see that this component converges, because cosine of something that's very, very close to zero is 1, logically. And you can see as we get really, really close, this piece also tends towards R for the cosine. But if it's also getting really, really close, the sine of the angle is not zero, because sine 0 is 0, but sine of something very close to 0 is effectively just alpha. So you can get that relationship, sine of alpha as alpha tends to 0 is nothing but alpha. You can do that because in mathematics we have a problem which says sine theta divided by theta. The limit of that as theta approaches 0 is nothing but 1. So you'll end up with this relationship where you can prove this with mathematics. And if I do that, what do I get here? As alpha approaches 0, what is that incremental piece that's happening just here in change in velocity? You can see here u times cosine alpha. That component effectively becomes u times 1 minus u divided by t, which is nothing but 0. With me so far? And then the acceleration component along the y-axis is nothing but u times sine alpha becomes alpha divided by t. So what we can see, this is the y component is here. So what we're now coming to realize is that when an object is in circular motion, constant velocity, that acceleration that we tried to understand is that because of which the force is there, right? And that force, we'll get to it in just a second because we have a mass. But by looking at the change in the components, we know there is a component of acceleration here, and the component of acceleration there is 0, 0. No acceleration there. But here we have a component of acceleration, and that is given there. And as in our notations that we're using with theta, we could just write the component of acceleration along this direction. So because it's happening here, it's not angular acceleration, it's just linear. So you can just write this as A is equal to, going back to the old notation, velocity v times angle or change in angle for change in time is change in theta, which is essentially theta prime, or omega here, which is angular speed. It's radial acceleration, okay? I'm just going to call it radial. And what is tangential? Tangential is 0. We don't have to worry about that. So we've got that. What might we do with this? We know velocity linear velocity is angular speed times radius. So we could just play with this a little bit and write the radial acceleration as r omega square. One way of writing that. We know omega is velocity by r, which would then also allow us to write this in another form, which is acceleration is velocity squared by r. That's another way of writing it. But notice that this is not second derivative of theta, because the second derivative of theta would be along the angle. This is not along the angle. This is effectively independent of the angle because it's along this line. So this is not the second derivative of theta. So do not confuse this for an angular acceleration in any form. The angular velocity is constant. So the second derivative of of the angle theta, or derivative of angular velocity, would be 0, right? Because velocity is constant. Right, so this was just a mathematical mechanism of calculating this for a very tiny change in the angle, just to see what's going on here. Right, I'm going to take the math away. I think you've arrived, or we've developed some of the interesting correlations. So let's just write this down here. We have acceleration is equal to omega squared times r. We can also write that as v squared by r. So that's another set of formula that are very important. I'll take all of this away, clean it up a little bit, and then we can get to the last part of what I want to cover in this video. So I've got that. I'll take that out too. Okay, so we know that much. So I have acceleration and I have mass. What happens? And therein lies the heart of this problem. So if I spin this, I know this string here is going to be tense, right? As I do this, it's on the horizontal plane, but that string is tense. It's not slack. It's not like this string, which is slack, which means there is tension, which means tension implies force, and effectively it is that tension which, if you remember, as I said, there is a straight line motion and there's some kind of a radial force that causes this thing to turn, and it's that tension that's causing it. How do you quantify the force along this line? Remember, this is a horizontal plane, no effect of gravity. So the way we would do that is the force acting here, right? The force vector here. So we've got the acceleration, and I want to write acceleration just to be clear so that we don't confuse it with this notation, just to demonstrate this is acceleration, in which case I can write force. Let me use another color along this direction. The force here is T, the tension on the string, and I can write that as mass times acceleration. So I could just write that T is equal to mass times, say, v squared by r. And that's the force that you get. And this is also a radial force. And it can be noted as the tension on the string, which is effectively the basis for this rotation, or this circular motion. Okay, I think that covers the good conceptual understanding. But let's kind of step in a little bit to another area. We'll extend it a tad bit, and this time we'll just introduce gravity a little bit, and then we'll do another video where we'll go into a little more detail to see the effect of gravity. But for now, let's take a case where it's still the horizontal plane. So now I have my horizontal plane, which somewhat, I'm going to draw it like that, right? And this is the center of that horizontal circle. What I want to do now is I want to have my little string there, right? That's my particle, and I want it to move along this direction. So it's similar to that. So it's similar to that. So it's still moving in a horizontal circle, but it's held by a string, and it looks somewhat like that. I'm not very happy with how I can draw things at times. So let me try to see if I can take another pass at this and do that. Not very pretty at all. Just wish I could make this a little smoother. Okay, we'll try this. There's my particle. Okay, there's my string. And there's the center of the circle. And to illustrate that this is the circle, I will make that a dotted line. Yeah, not ideal, but we'll live with this. The imperfect world we live in. Okay. Now this is an interesting case. So this is a horizontal plane along which I'm able to do this. That's my motion there, and that's horizontal. But the moment I do this, there's an interest, because now I have gravity acting down this way. And if my mass is m, then I know that mg is acting this way. Now in the previous case, it didn't matter because they were perpendicular. So mg would have been acting like this, and whatever was mg, it was impossible for it to create an effect either in this direction, or if it was perpendicular to the horizontal plane. Mg is always perpendicular to the horizontal plane. It has no effect along the horizontal plane, which is yellow here, but it has an effect along the vertical plane, which is in the blue color here. Now what is that effect, and how do we now say what is the tension here, T? So if the circle is of radius r, I want to keep my vertical plane in blue. So that's my vertical plane, and I call that H. Trigonometry can help us determine this angle. It's a vertical angle, so it's called theta. And as soon as I do that, there we go. So circular motion along, let's say, that path, which would automatically result in an acceleration here, A, which means I will have radial force R is equal to mass m times A. We know from previous calculations that that's nothing but mass times velocity, v, this is velocity, square divided by r. That works. So we know the radial force. If I look at it now on the vertical plane, right, I'm just taking a snapshot of looking at it on the vertical plane. I have an r, right, acting on the vertical plane. Let's say an r that acts along. Now I have an r. There's a t, and there's an mg. There's a theta. And with this, you should be in a good shape to resolve this. You can identify here that effectively any value of t should resolve to create a vertical equilibrium. On the horizontal plane, we are moving, and there is a radial equilibrium too, right? So the object is moving this way. Along the radial line, there is no movement. Effectively, it's not collapsing. The radius isn't collapsing. It's not spreading out either. It's not going up or down vertically, so there is no vertical movement. So you can resolve the forces that you have. So if I made a dotted line here, I could very easily say T sine theta is equal to mg, and T cosine theta is equal to radial force R is nothing but m times v square by r. I've resolved my t into these two directions and balanced the equations. I can now solve for t. I can do, as a matter of fact, I can also define theta by dividing these equations, sine and cos. T cancels out. I have tangent of theta. The mass cancels out, and I'll get g times v square divided by r. G is acceleration due to gravity, v is the velocity of motion, and r. So you can also develop some equations and solve some problems from there. So I think pretty much this sort of sets you up for the basics you need for circular motion. We've introduced gravity a little bit. What I want to do probably, and this is just for the A levels, but I won't do it as an advanced topic. I'll really maybe make a continuation of this video where we'll discuss the same circular motion, but this time, a vertical circular motion, because now we do have the effect of gravity coming in, because no matter what I attempt to do, there is a time when I'm going against gravity as I'm going up and with gravity as I'm going down. So you can see here as I'm doing that, if I didn't apply enough force, there's something that, if my wrist doesn't move well, you can see there, it drops off. So as soon as I come into a vertical circular motion, gravity likes to make a better, bigger impact. Here it's much more simpler because it's still horizontal. But we've introduced it. We'll go to the next video and we'll speak a little more about how gravity influences it, and then we'll do a little bit of math around that, and hopefully that will set you up well for A levels. I'm not going to do it as advanced. I'll just do it as a follow-up to this. But yeah, here you go. Important formulae, things to remember, and we'll see you in the next video.